Angular momentum. It's what makes the world go round. All right. So before we talk about angular momentum, let's review linear momentum because it's quite analogous to it. It's the rotational equivalent of linear momentum. And recall that we defined linear momentum. We gave it the letter p, lowercase p, with the vector hat on it, because it is a vector. And we said that p, by definition, is equal to the mass of an object times its velocity vector. And one of the things that we did, we said, well, let's see what happens if I take the derivative of this, okay? The derivative of momentum with respect to time. What if I'm changing the momentum of an object as time goes by? What are the consequences of that? Well, let's use the product rule here. It's the mass times the derivative of velocity plus the derivative of mass times the velocity. Okay, the good old product rule. Now, in the vast majority of problems that we work, the mass of the object that is being accelerated is not changing with time. There are a few exceptions to that. If you think about a jet engine, okay, you've got air coming in, you've got exhaust coming out, but the exhaust has more mass in it than the air coming in, right? Because it's burning fuel. It injects fuel, it ignites it, and that fuel goes out the back end. A rocket loses mass as it goes up. A hose, if you hold onto a hose and it's a high velocity hose, you know, you got the water coming out really, really fast, you feel a force pushing back on you. And that would be this term right here. But if your mass is constant with time, and that's usually what we do, then the derivative of mass with respect to time is 0, right? Because mass is constant. And so if that's true, you get m times dv dt, and of course we know that m, this is mass times acceleration, and this is what we call the net force acting on an object. Okay, so if the rate of change of momentum is our net force. Okay, so that's what we talked about before, and we're going to do the same kind of thing. Now I'm going to skip ahead a little bit, but let's think about what we call angular momentum now, or rotational momentum. Let's start off with a linear momentum again. Well, the angular equivalent of momentum, the angular analog of linear momentum, or angular momentum, we use the capital L to represent that. And that's just a new variable you're going to have to learn. Okay, it's L. Now let's use analogous variables. This is not a proof. We're actually going to prove it a little bit later. But what's the angular equivalent of mass? Yeah. I, rotational inertia. And what's the angular equivalent of velocity? Yeah, angular velocity. So this is one way to think of angular momentum. And by the way, this is true. This really works. Now, and the analogy part is true as well, but that's not a good enough explanation for why this is true. But there is rotational motion that objects have, even if they're just moving in a straight line. Now, let me show you an example. Imagine was I off screen there? Okay, I was okay. Imagine a roller skater, okay? And she's rolling, I'm just going to represent her as a dot, and we're looking down on her. And she's going with she has a certain mass and a certain velocity. But then there is, let's say that there's a pole right here. and this pole is kind of sticking up like this pencil is, right up out at you. And as she goes by this pole, she reaches out with her arm and she grabs it. Now she's on roller skates, so let's pretend that she's moving with constant velocity. These are magical, frictionless roller skates, okay? And you reach out and grab it. What is she going to do? She's going to spin around. Okay? Or you can think of this as just a particle that's spinning right here. And let's say I've got a little hook on it, and when it reaches here in a string, and then it's going to hook onto it, and it's just going to spin around. Okay? So let's think of what's going on there. Let's take a look at an object now that's moving in a circle. And it has the same velocity that it had before, but of course the direction of the velocity is changing, but the magnitude is going to be constant. So let's take a look at this. This is the velocity vector, and this is the mass. And this right here is the radius of the from the axis of rotation out to where the particle is. So it's spinning around like this, and here's R, and here's MV. Well, let's go back and think about, this looks a little bit familiar, because here we have an R vector and a linear momentum vector. We can actually, let me change this, because I wrote it as m times v, but what could I do? I could say that this is really the linear momentum vector, right? Which is, this object has a certain mass and a certain velocity. Now, remember that what we talked about last time when it comes to torque. Remember we said that torque, and where am I going to do this? I'll do this right up here, torque. Let's talk about torque for a second. Remember we said that torque, we use a tau to represent torque, by definition was R cross F, right? Okay, so and what this is this is, here we have an R, and then this is where the a force, and I think that we can visualize this if let's take a stick. Let's pin, here's a pin. I'm going to pin a stick to here. So this stick can rotate around this pin, but it can't translate. So this pin holds this thing, and this thing can spin. The stick right here can rotate around, but it can't move that way. Can't translate. So if I apply a force like this, well, here's what R is. R is from the axis of rotation, or the pivot point, to the application of the force. If I extend this out, this is called phi. It's the angle between the R vector. If I extend out the R vector, if I put the R vector and put it tail to tail with the force vector, that's the angle it makes. And so we get the cross product of R cross F. That is the definition of torque. And remember, we discussed dot products or cross products last time. If we have R like this and you cross over to F, my thumb is going to stick up right here if I use that right hand rule. And so this torque will be R F sine phi. And if I make this the I hat and this the J hat, and so K hat comes out of the board, then this torque will be in the, if I go R cross over to F, use that right-hand rule, my thumb is sticking up, which I'm saying is the k-hat direction. And so there we go. There's my torque from this. Well, I don't really have a torque on here, but I could certainly put one. Let's say that at the instant I'm looking at it, this is the momentum vector, but let's say that there's a force vector. Whoops. Let's put the force vector down like this. So I'm going to apply a force to it. Now this is let's say this is a tangential force. Let's keep it simple. So a tangential force is going to change my speed. And therefore it's going to change the magnitude of my momentum vector. Notice that a centripetal force will change my direction, but it won't change the speed of my momentum vector. It will change the direction of the momentum vector, but it won't change the speed I'm moving, or the magnitude of the momentum vector. And let's say that this force, this tangential force, let's say that that's the net force. How could I do this? Well, imagine you have a little airplane on a string and it's got a propeller on it and it's going faster and faster and faster. Or you can put like a little Estes rocket engine on here and fire, and it's going faster and faster and faster around this circle. Okay. Well, so anyway, I can measure the torque on here. This force, whatever's causing this tangential force on this object as it goes faster and faster around in a circle, okay, that torque is equal to R cross F, right? But we also said that, and if this tangential force is the net force, I just said that the net force is over here. I said that I can let the net force be the rate of change of linear momentum. So I'm going to do that. The torque on this guy is equal to R cross dp dt. Okay. Now, in this case, R is a constant, okay? But there's nothing wrong with putting this in the derivative operator. So I can say this is equal to d dt, oh, thank you, of R cross P. Now, if I were to actually do this, I could, oh, now, look what I've got here. I've got this very interesting quantity here, R cross P. Okay, well, let's keep going here. This is, if I apply the product rule to this, I get the first times the derivative of the second plus the derivative of the first crossed with the second. Now, in the example that I'm going to use here, and in most of the things that we're going to do, the R, the radius of the circle that I'm going around in, is not going to change with time. Let's just, for right now, let's just say that R is constant. Well, if that's true, then this term goes to 0. So I have R cross dp, which is just what I wrote over here. But so what a torque does is that it's changing the quantity. It's changing a particular kind of quantity. Now let's think what R cross P really is. Here I've got linear motion represented, but the R represents the radius of which it's circling. Okay? So really what R cross P is a measure of is how much rotational motion that particle has. And so what we do is we say actually let me So we're going to come up with a name for this amount of rotational motion. We call it angular momentum. So angular momentum we're going to represent it with an L. And by definition, at least for a particle, for a particular particle, it's R crossed with P. And if you want, you can extend that R cross M times V. So think about it. Here's how much stuff is spinning, right here, R. V is how fast it's moving, but R gives us an idea of where it is from the axis of rotation, right? The farther you are out from the axis of rotation, the more rotational motion you have. So, but anyway, this is how we define angular momentum. Okay, now I'm not here yet. We're going to get to I omega here pretty soon in terms of analogous variables. But, oh, that's weird. The fan on my computer is blowing the paper over. All right, move that over. Okay, now, any questions on that so far? You're sort of following the logical chain here. It's a lot to take in. Let me zoom out so you can see the whole thing. But it's very analogous to what we've done with linear stuff. Okay, well, what if I've got, here's my point of observation, and suppose I've got a whole bunch of particles. Okay, and they each have their individual little masses, and they each have their individual little velocities. Okay, so these are all have their own masses and their own velocities. This would be like a gas. Now, you know what I'm going to do to distinguish that? I'm going to put a little x and y axis here. And so here's my origin, and this is where I'm observing these particles. Well, what's the total angular momentum here? The total angular momentum is just going to be the sum of the individual angular momenta of each particle. And so if I want, what if these individual particles are under the influence of some outside force? Like what if there's gravity? So this has a force downward, and this has a force downward, and this has a force downward, and downward, and downward, okay? So that's going to change the angular momentum. Okay, but now this is equal to, let me change the order of that. Let me put this is mi, oh, wait, hold on. I'm being silly. Stop it, you're being silly. All right, R cross I cross MIBI for each individual little particle. Well, if I've got a force acting on these particles, then that force will change the angular momentum. And so you can say, well, the rate of change of angular momentum is just the rate of change on this whole thing here. Now this is just a sum, so what I'm doing is I'm operating the time derivative on each individual thing, and when I do that I get the torque. And so what we get, this is going to be the total net torque on the system of particles, and this is just going to be the sum of each torque. So they'll talk about that, and that'll lead to other things. Okay. And that's all. Okay. Now, one other thing here. Yes?
Do you know where Mrs. Harris's class is at?
Oh, they went, they're in the computer lab.
Computer lab?
Yeah. Okay, so now here's something really interesting. So anyway, this is for a system of particles. So it just means, hey, if you do it for one particle, it works for all the particles, you just add them up. Okay, no big deal.
Yeah, when you do Ryan R, you do DRDT, doesn't that get you velocity?
I'm sorry?
Like, a couple steps back when you do R, X, D, DT, and D, R, DV.
Well, in this case, R is the, well, actually, you're correct. R in these cases can change with time, okay? So the computation here becomes pretty crazy. But the concept, we're not really going to do this for a whole bunch of moving particles, like a star cluster or something that's all moving. We're not going to do that in here. But this will allow us to look at a rigid body. And,
Even with a rigid body, isn't R still a vector?
well, R is a vector, yes, but let's say this is a rigid body. That means that as the system rotates, R doesn't change with respect to the axis of rotation. And so it's not going to be part of our derivative. Well, I mean, it's dRdt is going to be 0 for each individual particle. So, oh, now I'm not sure if that's actually right. I don't know. Let me move on though. Okay. The one thing I want to show you is that even if an object isn't spinning itself, it can have angular momentum by this definition. Think about where we started. We had that roller skater approaching a pole. So here's a particle that's moving. It has mass and velocity, and it's moving like this. Here's my observer. This, if I say, here's R, so here's my observer, here's R, here's MV. Now, if this object is just moving with constant velocity here, well, by our definition, even if this object isn't moving with constant velocity, it doesn't really matter. This object at that instant in time has angular momentum with respect to that observer. Because you just go R cross MV. But here's what's weird about angular momentum. It depends on where the observer is, how much angular momentum it has with respect to that observer. I mean, what if the observer is right here? And so this is like this particle is approaching the observer. What is R? Well, R is from here to here. Well, what's the cross product of R cross MV in this case? Well, let's think about it. In this case, L equals R cross MV. Well, that's R times M times V times the sine of the angle between it. Well, what's the sine of the angle between an R right here and an MV like this? 180 degrees. What's the sine of 180? It's 0. So, with respect to this observer, the object has angular momentum. With respect to This observer, the object has no angular momentum. If you're an observer over here, the object has more angular momentum than it does. The farther you are away from this guy, from the path that this guy traces, the farther you are away, the greater the angular momentum this object's going to have, based on this definition.
Why is it that when you get farther away, the object has more angular momentum? Because it's going to be, across your field of view, it's going to be moving slower.
No, it's moving at the same velocity.
Yes, but it'll appear to be moving slower, since you'll have a wider angle of range of view.
Well, but it's mainly, well, M, when you look at the definition of L, this value doesn't change, this value doesn't change, this value does. R is now greater, and also the angle is more, compared to this, if you look at this angle, as opposed to this angle is closer to being perpendicular, and so it's greater. Now, let's take a look at this. Here's what I want you to see. This is like a perpendicular distance here. If the object is right here, we have R cross MV. All right, so that looks like that. Let's look at the object. Let's say the object is over here. And so here's my R vector. Here's my MV vector. But if I go out like this, it now can, draw. So here's my angle phi. And so we can extend this down. You know what? I'm getting a little. This is getting too messy, and I'm going on too long. So I'm just going to stop right here. We're going to get to. Also, I'm thinking about talking about conservation of momentum, but we'll do that in the next lecture. So anyway, just to summarize again. Angular momentum basically starts with our definition of linear momentum. If you think of an object that's rotating around, it has linear momentum at an instant in time. But if you cross that, you go R cross MV, you have an idea of how much rotational motion that particle has with respect to the center. And that R cross P we define to be angular momentum. And it works for a system of particles as well as a single particle. And then what we're going to eventually do, of course, is extend this to rigid bodies. But I went on way too long. Stop now.